So throughout this course, and indeed your previous course in quantum mechanics, you're fairly happy with the evolution of the state. So the state in quantum mechanics evolves according to the Schrödinger equation, and we've discovered that that means that it can be described by a unitary operator, the time evolution operator, which you can get straight from the Hamiltonian, just like you can in the Schrödinger equation. Because it's linear, if you have it in the position basis, say, the position basis wave function is related to the position basis wave function at a previous time by this fully general linear operator called the propagator, or sometimes the transfer matrix, or sometimes the Green's function. And this G is defined simply as the position basis version of the time evolution operator. Now the path integral formulation of quantum mechanics says that instead of finding it this way, instead of finding out U from Schrödinger's equation, it says you can find it out from these classical paths, all the possible ways you can go from one point to the next point, define a range of paths. You take the action of each of those paths, and that defines the phase. You add up all those phases, and you get an amplitude for going from A to B, which is all this is. This is just a complex number, so at some level it's just an amplitude. Now that's very non-intuitive, so we're going to prove that now. The way we're going to do it is we're going to expand that out. We'll do it in one spatial dimension, and we'll do it for a constant Hamiltonian, because the other generalizations are fairly straightforward, but it will complicate matters for now. So if we have a constant Hamiltonian, then we can actually solve this equation perfectly happily, and we've already done so. So it's just the exponential of the Hamiltonian. Now in order to proceed, we're going to break up time into small slices. So if we have a position axis, that might be our x-axis, and this is our time axis along here. Okay, so there's our origin. Then at each slice in time, we have to define an entire wave function. So there's a wave function. At a later time, we have a different one. And by breaking up our evolution into slices in time, we can begin to make approximations on the form of this. So we note that our evolution, to go from t0 up to t, we can break it into pieces very simply. So in other words, to go from t0 to t, we can go first to t1, then to t2, then all the way up to tn, and then up to t. Well, this is trivially true from the definition of the time evolution operator. It must work like this to evolve you from one time up to another time. But you can also show it's true directly from the exponential form, because the Hamiltonian trivially commutes with itself. If you have two terms of this form, then you can follow the normal rules for the exponential, because these two terms commute, and therefore it's just the exponential of the sum of the two, like that. And then this equation follows immediately. And what we've gained by breaking up our time evolution operator into lots of small pieces is that the time step for each of these pieces can get very small. Now remember that the time evolution operator is based on the Hamiltonian, which in turn is made of a kinetic energy and a potential energy part. And because these two parts don't commute, we can't factorize this exponential like we pull that together. So if we expand out the exponentials in those two terms in terms of their Taylor series, then we find that they're not identical, but they are identical up to the first order. And so this expression is correct up to order delta t squared. And then of course we can see that as we make these time steps smaller and smaller, we can start to ignore this term, and so that we can do this factorization in that limit. So now we're basically ready to get the form of the propagator. So the propagator can be gained from the expansion of the time evolution operator. If we expand out the time evolution operator with all of these things here, then we can stick in the completeness relation, which remember, in any complete orthonormal basis can be written just as the diagonal elements of that. And we're going to have to choose a different dummy index for each time we put it in. So that'll give us, we then substitute in our expression for u into each of these steps and take out all the order plus delta t squared terms, and we get where delta tn is going to be t minus tn, and we go all the way down to delta t naught being t1 minus t naught. Now we know how to apply this to there because this is a function of the position operator and these are position eigenstates. So if we do a Taylor expansion of this, all of the position operators just give us out an eigenvalue, and we get exactly the same function, except instead of being the x operator, we end up with xn. And because it's just a complex number, we can take it all the way out. And because it's just a complex number each time, but they're all exponentials, then we just get the sum of the terms inside, where we've defined x of 0 just to be y. Now we can't do the same thing for the momentum operator, because the momentum operator acting on the position operator actually does a lot of damage. It's not just an eigenvalue. So one of the best ways to deal with that is we're going to deliberately put in momentum states into there. How do we do that? We insert the identity operator, and again we use the completeness relation, and once again we're careful to use a different dummy index each time we insert the completeness operator in there. And now we can do the same trick. We can just apply this exponential to that operator, and because these are the eigenstates of this operator, we're just going to get a function. So we're going to get that complex number coming out, going to get that n times, and because they're all exponentials, they'll sum up just like this one did. Now all of these elements here are just inner products between position eigenstates and momentum eigenstates, and since we know what the momentum eigenstates are on the position basis, then we know that all of these things are just exponentials. So when they're that way around, we'll have the plus exponential, and when they're that way around, we'll have the minus exponential, because that's the Hermitian conjugate. So we're going to get a long sum out of here. I'm going to take out a factor of I and h bar and a delta t from each of the sum elements. So what I've done there is I've had to associate x of n plus 1 with just the x in the same way that I associated x of 0 with y. And then I've got this term here, and this term here, you'll note that looks exactly like the Hamiltonian for state J. And we'll have a large number of factors of 1 on square root 2 pi h bar, and indeed we'll have 2n of them. And now we're ready to go back to the continuum limit. So what we've done, remember, is we've broken up our evolution into lots of little tiny time slices, and now we're going to try and put it back together again. So the limit that delta t goes to 0, that term will go away. The limit that delta t goes to 0, what we have to find here is precisely the derivative. So this is xj dot. And if we look at that, that's pj xj dot minus the Hamiltonian of pj and xj. And if you remember the original definition of the Hamiltonian, that is precisely equivalent to the Lagrangian. So this thing in there is just the Lagrangian at xj and xj dot. And what we're doing is we're taking the sum of all those Lagrangian elements multiplied by the little steps in time. And of course, the limit that these steps in time get arbitrarily small, this is just the Riemannian sum, and so this is just the integral. So what we've got here is the exponential of the integral of the Lagrangian. And that is precisely, of course, the action. And so this thing here is some kind of large number of integrals. What are we integrating over? We're integrating over all the possible positions that we might take at each slice and all the possible momenta. Let's have a look at that. Let's just look at the positions, I guess. So here again is our time axis. Here's our position. And here are our little slices in time. So supposing we start here, that's our x. And supposing we're going to finish there, that's our y. Then what we're talking about is we're talking about every possible value for here. So we're talking about going from here to each of these values. So if you think about it, that's just paths like that. And then we're talking about going from every one of these values to every one of those values. So I'll just put in, say, 3 of them, and all the crossed ones as well. And so on and so forth until you bounce every possible way you can get to the final end. And you can think of that very easily as a path. So each possible way you can link these lines, link all these points, is a path. And when we're integrating not over the positions but also the momenta, then it's just an arbitrary path in phase space. So these paths don't have to follow any kind of logic. They can be faster than light. They can be as crazy as you like. They don't have to follow any kind of laws of mechanics. But if you add them all up with the phases associated with their action, then what you get is the propagator to get from the original point to your final point. And so this is defined as, if you will, the sum over all the paths. And we have our result.